We will be looking today at logarithmic functions and exponential functions and how those are related with lesson 7.3. And I'd like you to pause this for a moment and just take a look at the warm-up. Okay, looking at the warm-up, 4 to the negative 3 is just 1 over 4 to the positive 3, or 1 over 64. With part B, 16 to the 1/4 is just looking for the quartic root of 16, which is 2, because we know 2 to the 4th power gives us 16. 10 to the negative 5, or 1 over 10 to the positive 5, is just 0.00001. And then 2/3 to the negative 3 is the same as 3/2 to the positive 3, or 27 over 8. When we take a look at E, it's just saying that we've got a power with a base of -2 and an exponent of 4. So if we want to be able to evaluate that, that's just -2 times itself 4 times, or 16. When we take a look at this next page, it's looking at the exponential form of a number and the logarithmic form of a number. And we can see how those are related. And they have the same definitions. Both of these expressions are saying the same thing. A base raised to a given power gives us a specific number. A log is just another way of looking at that. They're saying, what number do we have to raise our base to in order to get A? So they're saying exactly the same thing, just in a different format. And when we look at the exponential function and the logarithmic function, they are inverse functions. So when we take a look at this first example, and we're taking an exponential form of a number and rewriting that in logarithmic form, the base of our number is the base of our log. So, I would say log base 3 of number 243 is our exponent. So this is just telling us that 5 is the number that our base 3 has to be raised to in order to get 243. So I'd like you to pause this right now and try some of the other problems, and then we'll take a look at those. So if we take a look at these next problems, here, we're saying that 1/2 is the exponent that 25 needs to be raised to in order to get 5. 4 is the exponent that 10 has to be raised to get 10,000. 6 raised to the -1 power gives 1 over 6. A raised to the B power gives us C. 9 raised to the 2nd power gives us 81. 3 raised to the 3rd power gives us 27. And then, X raised to the 0 power gives us 1. So, as we know, any number raised to the 0 power other than 0 will give us 1. Okay, here with this table, we're going to look at, when we're given something in logarithmic form and we want to rewrite that in exponential. So once again, since they're both saying exactly the same thing, here we know that a logarithm is just an exponent. And here's the base of our logarithm. So we're saying 9 raised to the 1st power will give us the number that we're looking for. Here, our base, we're saying, and this really should have a 9 written there. Base 2 raised to the 9th power gives us 512. And you can take a look, certainly, and multiply it out by itself 9 times and check and see that you do have that written correctly. Now I'd like you to pause this and take a few minutes to complete this table. So converting this, we certainly have our exponent of 1/3 and our base of 8. 8 to the 1/3 power gives us 2. In the next one, we have 4 to the -2 gives us 1 over 16. Our base raised to the 0 power gives us 1. Our base of 10 raised to the 1st power gives us 10. And then our base of 12 squared gives us 144. And then our base of 1/2 raised to the -3 gives us 8. And as I said, you can easily check all of those and know that you've written it correctly. As we said, a logarithm is just an exponent, so all of the rules that apply to exponents also apply to logarithms. And a couple of the very basics, I mean there's certainly many more, but a few of the very basics would just be a logarithm of base b. And that's just saying that if you have a log with a base of b and you're taking the log base b of b, that's just going to be 1, because you're just saying, what power do I have to raise b to in order to get b? Well, that would be 1. And then a logarithm of 1, anytime you have log base b of 1 equaling 0, it's just saying, what do I have to raise b to in order to get the number 1? Well, anything raised to the 0 power will give us 1. So, some of the very basic special properties apply to both. Common logarithm, a logarithm with a base of 10. When you see log, something like this, log 5, and you don't see a base explicitly written, it's assumed to be 10. So when you see something like this, and you take a look at that, it's a matter of saying, okay, what exponent do I have to raise base 10 to in order to get 0.01? And the answer would be -2. So I know that log base 10 of 0.01 is -2. That's the exponent that you have to use to raise 10 to -2 to get the number that you want. So I'd like you to pause this and take a minute to try the other problems. So in the next problem, we're just saying, what is the exponent that we have to raise 5 to in order to get 125? And that would be 3. 5 to the -1 power gives us 1 over 5. And then once again, we're implying, that's a base 10. 10 raised to the -5th power gives us 0.00001. And then 25 is our base. 25 to the -1 gives us 0.04. Okay, because the logarithms are just inverses of exponents, if we've got an exponential function, we know that the inverse function will be logarithmic. And here's an example right here. We've got an exponential function y equals 2 to the x power, and when we take the inverse of that, or rewrite that in logarithmic form, we have y equals log base 2 of x. And when we graph both of those, you can see it's just a reflection across the y equals x line, and we can see that the domain, when we look at our initial exponential function y equals 2 to the x, the domain is all real numbers in the range. The y's are greater than 0 because our x-axis is the asymptote. When we graph the y equals log base 2 of x, our inverse function, we can see that our domain would be all values, x is greater than 0 because our asymptote is now the y-axis, and the range is all real numbers because we're not limited for our y values. So I'd like you to take a look at number 4, and we want to be able to graph that function, and we are using the values given, which are also listed in our table right here. So, if we take 1.25 to the -2 power, that is 0.64. And then -1 raised to, if we take 1.25 to the -1, that's just 0.8. If we take 1.25 to the 0 power, we have 1 to the first power is 1.25. And if we square 1.25, we have 1.5625. And I'd like you to take a minute now and graph those points. So if we graph those points, we can see that we've got an exponential curve, and as we move to the left on this graph, or as our x values get smaller and smaller and smaller, we will approach the x-axis, which is our asymptote. So it won't cross the x-axis, but it will get closer and closer. So when we take a look at this, our domain, or our values that are possible for x, are all the real numbers, but the range is going to be all y's such that y is greater than 0. So when we now rewrite this and we create our inverse function written in logarithmic form, once again, we're still saying exactly the same thing. We're saying, okay, here is our exponent. That's our log. And the exponent is -2. And, we are taking a look at, what number that would create. If we take our base and raise it to the -2 power. So if we take 1.25 raised to the -2 power, what number do we get? And we have 0.64. And, as we would expect, we would just reverse our x and our y values. So I'd like you to graph these points now. So if we graph our inverse function, or the logarithmic function, we can see right here that it's just reflected from the exponential function across that y equals x line. And now we can see that as we give smaller and smaller x values, it is going to approach the y-axis now. That is our asymptote. So when we take a look at the domain, our x's will be values such that x is greater than 0. And then the range is going to be the set of all real numbers, because we have no limitations, in the y direction. So I'd like you to take a look at the next problem, and I'm going to, if you would pause this for a minute, and I'd like you to take a look and try to fill these out and graph that problem. So if we take a look at our exponential function, 1/2 raised to the x power, certainly 1/2 raised to the -2 is just 2 raised to the +2, or 4. Using -1 as our exponent gives us 2, 0 gives us 1, 1 gives us 1/2, 2 gives us 1/4. And we can see, graphing this, that as our x values get larger and larger, we approach the x-axis, which is the asymptote. So it's never going to cross over, which tells us certainly that our domain is a set of all real numbers, but then the range is all y values such that y is greater than 0. Now I'd like you to take a look at the next piece and look at the inverse function, and we're going to rewrite that as a logarithm, and we're going to take a look at the values and then plot them. So I'd like you to pause this and try that. So looking at the logarithmic function, certainly we're just reversing our two values, our x and our y value from the exponential form, because we know that our x value being 4, that's the number we want, and we're saying what value do we raise 1/2 to be able to get 4, and that's -2. So if we continue on down and then plot these points, we can see that this curve is just a reflection of our exponential curve, and it approaches our y-axis as we get closer and closer to 0 with our x values. So our domain, the x's are going to be greater than 0, and our range will be the set of all real numbers. So if we go on to the next page and actually look at these problems, they've given us hydrogen ion concentrations for different food items, and we want to calculate the pH value, and they've given us this formula. So you're simply using the formula they give you. If we look at milk and we want to find the pH value of milk, then we're just taking opposite of the log of the hydrogen concentration, which for milk is 1, 2, 3, 4, 5, 6, 2, 5. So when we do that, you use your calculator to find the log. We know that that's approximately 6.6 for our pH value. And pH's range, I believe that's between 1 and 14 to give some indication of where that's falling. So I'd like you to take a look at the rest of the table and pause this while you complete. So completing the rest of the table with tomatoes, the pH being 4.5, iced tea at 3.8, and lemon juice being 2.2. Certainly, that indicates that the scale, as you move closer to 1, is, acidic. Moving the other direction would be your base, because certainly you would expect milk to be not quite as acidic as lemon juice. So if you'll start the homework problems, and you can work your way through those.